In this exercise, we have to apply the SLD resolution strategy over this proof of logical consequence. So we have to prove that the conclusion formula C is a logical consequence of the two premises. As always, in case of resolution, first we have to translate the premises to CNF one by one. And furthermore, we have to translate the negation of the conclusion formula to CNF. For the first premise, we can see that the formula is a negated implication. Therefore, the law of contraposition can be applied. Therefore, we turn the implication into conjunction, where the right-hand side is negated, and therefore we can apply one of the De Morgan laws to this part of the formula. So basically, the negations disappear, and we get a disjunction. This is already in CNF. Let's continue with the second premise, which is a simple implication. Therefore, the left-hand side must be negated, and we can also apply one of the De Morgan laws. So basically, or finally, we will get not Z or not Y or X. And well, as you can see, we have two disjunctions. Therefore, this pair of parentheses can be eliminated. So basically, we get one single clause inside this CNF. Finally, let's translate the negated conclusion into CNF. Yeah, this is easy. Not X or not Z. Okay, let me enumerate all the resulting clauses here. Clause number 1 is a unit clause Z. Clause number 2 is X or Y. Clause number 3, not Z, not Y or X. And finally, clause number 4, not X or not Z. So these are the input clauses we got. Input clauses for the resolution algorithm. And it's not an accident that I highlighted this fact that these are the input clauses, because when applying SLD resolution, input clauses play a very essential, very important role, as you will see that. SLD resolution. So we must run the SLD resolution over this input clause set. And we know that SLD resolution has a drawback. It's not complete over any kinds of clauses. It is proven that SLD resolution is complete over Horn clauses. That is, if we have an input clause set which consists of not only Horn clauses, then it might happen that we cannot derive the empty clause, even if the input clause set is unsatisfiable. It can happen. This is what incompleteness means. But if we could translate all our clauses to Horn clauses, then it is guaranteed that SLD resolution will be able to derive the empty clause if the input clause set is unsatisfiable. Okay, let's look at our input clauses. Are all of them Horn clauses? Well, not really. Clause number 2 is not a Horn clause. Actually, what is a Horn clause? A Horn clause is defined as a clause which can contain at most one positive literal. So if you look at clause number 2, it contains two positive literals. X and Y are not negated, they are positive. So clause number 2 is not a Horn clause. As a side note, all the other 3 clauses are Horn clauses. Of course, clause number 1 is a Horn clause. Clause number C is also a Horn clause because it contains only one positive literal X. And clause number 4 is also a Horn clause because it contains no, it means 0 positive literals. And you see, by definition, a Horn clause can contain at most 1 positive literal. So 0 is also okay. Okay, so what can we do? Well, let's try to turn clause number 2 into a Horn clause. How to do that? Well, of course, we should try to negate one of its literals. Let's try to negate X like that. So this is now a Horn clause, but be cautious. This kind of negating of my Boolean variables must be consistent. So we must then negate X everywhere. We must negate X in clause number 3 and also not X in clause number 4, where the 2 implications are eliminated. And after this, let's look at our clauses. Are they all Horn clauses? Yes. Now, all of them are Horn clauses. Let me note that this translation of clauses into Horn clauses not always possible. Fortunately, now it was possible, and therefore we can be sure that SLD resolution will be able to derive the empty clause if this input clause set is unsatisfiable. Okay, so let's try to derive the empty clause by using SLD resolution. As always, we pick 2 clauses at the beginning. Let me pick clause number 1 and 4 and resolve them. The resolvent now is X. Okay, what to do next? Well, let me note that the letter L in the middle of the name SLD suggests that SLD resolution is also a linear resolution strategy, and actually it is. So we have to construct linear resolution derivation, which means we have to pick the latest resolvent every time and look for a side clause. For clause number 5, we can choose 2 clauses, clause number 2 or clause number 3. Let's pick the shorter one, clause number 2, and generate a resolvent, which is now Y, exactly. Then, again, since we are constructing a linear resolution derivation, we have to pick the latest resolvent and look for a side clause. And of course, we can only pick clause number 3 at this time, which generates a new resolvent, not Z or not X. Okay, let's pick clause number 7 now and look for a side clause. And clause number 5 is really tempting to choose, but we cannot choose. We must not choose clause number 5. Why is that? Because SLD resolution defines a very strong constraint, restriction. SLD resolution restricts us to choose a side clause only from the set of input clauses. Again, you are allowed to choose a side clause only from the input clause set. This means you can only pick now clause number 1 or 2 or 3 or 4, and none of the rest of the clauses. Okay, so we must not choose clause number 5 because clause number 5 is not an input clause. So which input clause can we choose in this case? Yeah, we can choose clause number 1, and the resolvent in this case is not X. Again, it's so tempting to choose clause number 5 as an input clause, but we must not. Therefore, well, the only side clause we can choose is clause number 4. The resolvent is not Z. And finally, we can choose clause number 1 as a side clause and generate the empty clause. To summarize, we applied SLD resolution, which is a restricted version of linear resolution, and the restriction is about choosing the side clauses only from the input clause set. We derive the empty clause, which of course means that the clause set is unsatisfiable, and by proving this, we also prove that the conclusion formula C is a logical consequence of the two premises.